Okay, so prior to the break, we talked about the correlation coefficient R. And we gave kind of these general rules saying positive, the sign of R is the sign of the relationship, and the magnitude of R is the strength of the relationship, okay? Sign or direction, I should say, I'm sorry, is the direction of the relationship. This should already be in your notes. And the magnitude of R is or describes the strength of the relationship. And again, R only makes sense for linear relationships. Okay, it can be calculated. R is just going to be calculated by a computer, okay, or there's a formula that a computer uses to calculate R. We will not learn how to calculate R ourselves. It's a rather tedious calculation. So we will not learn how to calculate R ourselves in the class. But we should also keep in mind that R only makes sense for linear relationships. It exists for any pair of numeric variables, but it only makes sense for linear relationships. Okay. Okay, so in our class, we will not learn the process to calculate R. Okay, so R, the correlation will be calculated for you by a computer or provided to you in the problem. Okay, and then how do we know if a relationship, how can we see if a relationship is linear? Do you guys know? Okay. The only way we can see if a relationship is linear is we create a scatter plot. And look. There do exist methods, you know, maybe in a higher statistics class, but the idea of creating a scatter plot and looking is really our best method here, okay? As people, we have a general sense of pattern recognition that can't really be taught with formulas and things like that. You know, how do you know if something is a face? You just look at it and your eyes recognize faces, right? This is just kind of an automatic thing that our brains do. and in this case, how do we know if a relationship is linear? Well, we have to create a scatter plot, and then our eyes do a lot of the kind of the processing. Our eyes and brain will say, oh, that looks kind of like a straight line. That does not. And studies have been shown that humans can, recognize with great accuracy what computers can, computers verify and things like that. So this method is just good enough. Eyeball it. If it looks like a straight line, then we're good. If it doesn't, then treat it like it's not linear. Okay, so now we're going to get into modeling linear trends. So this is section 4.3 in the text, and this is all about modeling linear trends. Okay, so just imagine this idea of modeling, okay, is as if you're going to try to create a simplified version of the world. Okay, so if you wanted to make a game where you're like simulating life or something, okay, you're not going to be able to replicate everything that you can do, but you might be able to just create kind of a toy representation of things, how things go, right? So maybe there's like a role-playing game where you go to school and maybe you can't do everything, but you're just kind of getting a general idea of what happens. And so this is what we're essentially doing. We're trying to create a relationship, a representation or a model of a relationship between two variables. Okay, so we are trying to create a model or representation of an actual relationship between two numeric variables. Okay, so for anything where we can create a scatter plot, we can also try to create a model to capture this this relationship. So maybe so if we looked at a bunch of different people, okay, so if our data is people, and let's say our x variable is someone's height, and the y variable is their weight, what kind of relationship do you think we'll see? What's the direction? Direction will be positive, okay? In general, people who are taller, have high height, tend to have higher weight. People who have lower height, are shorter, tend to weigh less, have lower weight. Okay, so that will be a positive relationship. How strong of a relationship will we have, though? I would say it's not going to be super strong, okay? Maybe just a moderate strength, okay? Because if you think of people, just think of all the people you know who are around the same height. So think of people who are like 5'10" or 5'9" in your brain, okay? Do some of them weigh a lot more than others? Yeah, okay. If you can think of people, who you can probably think of several different women who are maybe all around 5'5" or something, and some of them will weigh more than others, okay? And so because there's quite a bit of spread for each of these height values, we don't have a very strong relationship, okay? So it's just a moderate, okay? But we might want to create a model of this relationship, okay? So maybe I should just draw some fake data here with some spread, right? So we're going to have a positive relationship, but there's going to be some spread here. So we can create a model of this relationship. And what we're going to do is we want to predict the weight of someone. A person's weight based on the person's height. Okay, and of course our predictions won't be super accurate or super precise, but you know, if I tell you somebody is 5 feet tall, your prediction would be different than if I told you here's another person who's 6 feet tall, okay? Or for those of us, our friends from the metric system, if I say someone's around 150 centimeters, your prediction is different if I said this person's 180 centimeters, okay? So your prediction for weight would be different based on the information you have about height, okay? So how should we make the predictions? That is the model that we're going for, okay? So in this section, we're creating linear models, okay? Or straight line models. So if you think back to algebra, the equation of a line is defined by a slope and an intercept, right? You guys remember this from algebra, slope and intercept? Okay, so the same thing here, okay? We're going to have our predicted y is equal to an intercept plus a slope times x. Okay, so our predicted value for y is going to be equal to an intercept plus a slope times x. Okay, and the symbols that we use to show that this is our predicted y, we put a little, this is called a hat. Okay, we put a little hat over y, and the symbol for intercept is going to be a, and the symbol for slope is going to be b. So I've got y hat equal to a plus bx, where a is the intercept and b is the slope. Okay, and so this gives us an equation of a line which is simply a model of the relationship between x and y. So this equation of a line is a model of the relationship between x and y. Copy that down. Next slide, okay? Okay. Yes?
Why in the book they don't show it as y hat?
They don't show it as y hat. You know,
they don't put the hat symbol of the y under the regression line.
Yeah, I see what you're talking about. I don't know. You know, some books use slightly different notation. I think it's more correct to use the hat, but I guess if it's left off, it's okay. I feel like I suddenly got super loud, but okay, well, I'll just whisper over here. I don't. Yeah, I think there's like an auto gain on the sound system, and so sometimes it just amplifies for. It's not a very good auto gain. Oh God. Okay. All right. So here's we're gonna do a running example. Okay. And what we are doing is we're going to create a model that relates the thickness of a book. Can you hear me at all now? Okay, that relates the thickness of a book, which is going to be our y variable, based on how many pages are in the book. Okay, so in our case, x is known as our predictor, or also the independent variable. Okay, this is the variable we use to make a prediction. And y is the response, also called the dependent variable. Okay, and this is the variable that we are predicting. Okay, and I'm going to create a side note here. Okay, and this is, we're just going to say the quote best fit line will have these properties. Okay, the slope, you guys remember what the letter that we use for slope is? Yeah, the slope b is equal to r sy over sx. What is r? R is your correlation, okay? So you should know that. Sy is the standard deviation of the y variable. And Sx is the standard deviation of x. And the intercept, yeah, I'm going to run out of space here. A is going to be equal y bar minus the x bar, okay? Y bar is the mean of y, the mean of the y values. What is b? B is the slope, so you have to calculate the slope, okay? So b is the slope you just calculated. And x bar is the mean of x, mean of the x values. Oh, well, that's not really a side note if it takes up all this space here, huh? Okay, so, but in our running example, the slope and the intercept have been calculated for us. But if you had to, you could calculate the slope and intercept yourself, okay? Because we know how to get the mean of some numbers, right? So we can get y bar if we need to, and we can get x bar if we need to. R is always going to be provided to you, and you also know how to find the standard deviation of a set of numbers, right? So you would take your y values and you'd find your standard deviation of the y values, and you would take your x values and you'd find your standard deviation of the x values. So if you had to, you could go and calculate these yourself. But in our example, these will be given to us. Okay, and you can always assume R, the correlation, is always given to you. I'll never ask you to do that yourself. Okay, so anyway, if I may go on to the next slide. No, okay. Then I won't, I'll wait. Are we okay now? Yes, okay. Okay, so again, we want our y is going to be the thickness of a book and x is the number of pages in the book. Okay, so we would expect a positive relationship, right? Okay, so the thickness of a book is measured in millimeters, okay? All right, and so we write predicted thickness equal plus or another way, we could also write thickness, predicted thickness this way. This is also another way of writing that, putting a big hat over the word thickness. Or you might also just see it written this way, y hat equal to 6.22 plus 0.0366x. So all of these are ways to say the same thing, okay? Is that okay? All right, so what is the intercept in this model? What is the value of our intercept here? Yeah, our intercept is 6.22. And what is our slope? And our slope is 0.0366. Okay? Quick check, I know I already wrote this in your notes, but so don't look at your notes. Which is the response variable. What is the response variable? The y is the response variable, so our thickness is the response variable. What is our predictor? Number of pages. Okay, the predictor is our x variable, it's the number of pages. Okay, so we'll talk about the interpretation of the slope. Okay, so what does the slope mean?
The angle of the line?
Yeah, okay, so in,
Rate of change.
I'm sorry?
Rate of change.
Yeah, rate of change. Okay, so let's talk about this, right? What does the slope mean? So remember, we're trying to relate the number of pages to the thickness. Okay? So the slope relates the number of pages to the thickness. Slope relates x to y, or in our case, it relates pages to thickness. Okay? And what we're saying is that when we increase x by 1, okay, so here's kind of the interpretation. If we increase x by 1, our prediction for y changes by the amount of the slope. Okay? So what does it mean to add 1 to x? What is x? X is the number of pages, so adding 1 would be adding a page to the book, right? So if we add 1 page to the book, our prediction for how thick the book goes up by how much? It goes up by 0.0366 millimeters, is what we're saying. Okay, so adding 1 page increases our prediction of the book thickness by 0.0366 millimeters, which kind of makes sense, right? You add 1 page, you're not going to expect the thickness of the book to change very much, but that's what we have here. Okay, so adding 1 page, so that's adding 1 to x, increases our prediction of thickness by 0.0366 millimeters. Is this interpretation of the slope okay with everybody? Okay, because it's very important that we understand what these regression lines mean. All right, I'm gonna go. Can I go to the next slide? Yes. Okay. Our intercept is 6.22 millimeters, or just 6.22, right? And then so we have, again, I've got thickness. I'm just copying this over, you don't have to. 6.22 plus 0.0366 pages. Okay, so the intercept is our prediction for y when x equals 0. Okay, so this is kind of the generic interpretation of the intercept. It's our prediction for y when x equals 0. So in the context of this example, it means if, what is x? if pages were 0, so what does that mean? If you have an empty book, or just the covers, there's no pages inside the book, how thick do we predict this book to be? We predict it to be 6.22 millimeters thick. That's what this means. Okay, so if a book had 0 pages in it, we predict that the book will have a thickness of 6.22 millimeters. Okay, it's our prediction for y when x is 0. Is that okay with everybody? Yeah? Okay, so let's try an example here. So I'm gonna write something up, okay? So what we're gonna do is we've got we are looking at several cars, looking at used cars. Okay, and we're going to relate, we relate the age of the vehicle X to the price of the car, of the vehicle. Y, okay? So we want to predict price based on age. Okay, and so I have this equation, value or price is equal to 21375 minus 1215 age. Okay, so I'm going to ask a few questions. What is the independent variable? What is the response variable? Okay. What is the slope? And what is the interpretation of the slope? Okay. And then we'll ask what is the intercept? Okay, and its interpretation. Okay, and so I would like you to look at this equation and answer these if you can, okay? And so I should make a note that we will say we created a scatter plot and a linear model is appropriate. Okay, so go ahead and take a couple minutes to answer these questions. I'm going to pause the video if you're watching on YouTube, so I advise you to pause the video as well so you can answer these questions yourself. Okay, let's take a look at each of these answers. Okay, well, so remember, what are we trying to model? We're trying to relate the age of the vehicle to the price of the vehicle, right?
Yeah.
So in general, if you just somebody asked you, well, what kind of relationship would I expect between the price and the age of a vehicle? What would you say?
Older, less valuable.
So in general, unless we're talking about classic cars, but in general, older cars are going to be worth less than newer cars, right? So as a car gets older, its value, it goes down. That's what we're expecting, okay? Okay, so what is the independent variable? Age of the car, right? So age of car, you just want to write age, that's fine. And the response variable?
Value of car.
The value of the car, okay? If you just write value, that's also fine. Okay? What is the slope?
-1, 2.
The slope is negative 1215, okay? So remember the equation we say is y hat is equal to a plus bx, right? And in our case, we're doing a subtraction, so essentially we're adding a negative 1215, okay? So that's the slope, minus 1215. Okay, so far so.
Can you explain that again?
So basically, if it's negative here, your slope's going to be negative. Okay, it's because we write this as our equation of a line. I think I have this on a couple slides back. I said is y hat is equal to a plus bx. Okay, so here essentially I'm subtracting 1215, but that's the same thing as adding a negative 1215, right?
Mm-hmm.
So that's why I have negative 1215 here, because subtracting is the same thing as adding a negative. Okay, so what is the interpretation of the slope?
21.
Yeah, so if we flip back, we say, what does the slope mean? The slope is if we increase x by 1, our prediction for y changes by the amount of the slope. Okay, so in our example, what does it mean to increase x by 1? What is x? X is our age. So that means if the age of the car goes up by 1 year, we predict the value of the car to what? Decrease by $1,215, okay? So that's the interpretation of the slope. If the age of the car goes up 1 year, okay, so that's adding 1 to x. Okay. Our prediction of the value so our prediction of y changes by the slope, so our prediction of the value goes down $1,215, so $1,215. Does that make sense? Okay. So study this example because you'll need to do something like this on the quiz. Okay, yeah.
So if you have it written 21,375, so if the age was 0, then we're saying that the average cost of the new car.
So yeah, well that will be our intercept, right? So our intercept is this number, 21,375, and the intercept is our prediction for y when x is 0. Okay.
Sorry, I didn't know you didn't get there.
Yeah. We're doing that right now. Okay. So the interpretation of the intercept is our prediction for y when x is 0. So what does it mean for x to be 0? It means you have a new car, right? So this 21,375 is our prediction for the value of a new car. Okay. 21,375 is our prediction when x is 0, or in other words, we predict a new car to be worth 21,375. There you go. Okay. Next slide, okay? No, okay. That's why I ask. So highlight this example in your notes, I'd say. All right. How about now? Let's see how the Yankees did. Okay. Yeah, they were down 3-0 when I last checked. Nope. And indeed the game ends 3-0, so the Astros move on. Huh?
How many chapters will we go through before the midterm?
We'll get through chapter 6. Okay. The midterm covers 1 through 6. Yes, question?
I'm sorry. May I just clarify where you have the values, the hat value equals 21,375. Is that 21,375 minus 1215 times the age? Is that how I'm reading it correctly?
Yes, yes. We take 1215 and we multiply it by age. Okay? So yeah, I'm gonna take this and we're actually gonna look at this on the next slide. So actually, I'm gonna just copy this over. So now that I have this, here let's. So I'm gonna go to the next slide here. Right here, not here. We go. So now I'm gonna ask you make a prediction for the value of a car that is 5 years old. Okay, so age is equal to 5. Okay, and so what are we going to do? We're going to just plug in the number 5 into this thing. So I got value hat equal to 21375 minus 1215 times age, which is 5. Okay, so 1215 times 5, this is 6075. 21375 minus 6075 gives me 15,300. So this means we predict that a car that is 5 years old will be worth 15,300. So if you have a 2010 Honda Civic, we predict it to be worth 15,300 or whatever, okay? Something around there. 2010 is already 5 years ago. Can you believe that? What was the #1 single of 2010? Let's ask. #1 single of 2010. Let's just see. Billboard Hot 100 2010.
Right in the top 5.
Kesha, TikTok. What?
What made the top 5?
Top 5. Okay, let's see. You know what? Oh, you know, it's just it just tells me the calendar. Wait a second. Okay. So TikTok, Rude Boy, California Girls. So a lot of Katy Perry here. So yeah, Rihanna, Rude Boy, Katy Perry, California Girls, and Teenage Dream. Far East Movement, Like a G6. Eminem featuring Rihanna, Love the Way You Lie. people, and then at the end of the year is Firework by Katy Perry. So. Okay. Anyway. Yes.
We have questions down here.
Okay. Question. Yes, that's more important than Katy Perry.
Yeah. The 21,375.
Yes.
Is that's the value, correct?
That's the intercept.
That's the intercept.
Yeah.
The intercept is always going to be given to us?
Yes, so the model of the regression equation of our model is given to us in these problems. I had like a little side note that says if we had to calculate the regression model, we can do it. The formula for the slope is this, and the formula for the intercept is this. I think in most of the problems in the textbook, the regression model is given to you. There might be one or two questions in the text where you have to calculate the slope and intercept yourself.
And also the slope will always be given to us?
Yes.
This time.
Yeah.
Can you explain the regression model? What does that mean?
So the regression model is the way we relate an x value to a y value, okay? And it's just kind of, we're relating it with the equation of a straight line.
Got it.
Yeah. So the value of a car is determined by a lot of things, okay? But if you know the age, that gives you a good sense of kind of the value of the car. Of course, you know, the brand of the car is going to have a significant impact as well. But in terms of the value of used cars, probably a big thing that would determine it would be age, because age also gives you an idea of mileage. It doesn't tell you everything. You might have old cars with low mileage or newer cars with lots of mileage, but age gives you a general idea of things. So we could create a regression model relating value to mileage, okay? We cannot create a regression model relating value to make of the car. Why not?
Oh, that's a good question.
Because each make has different model.
Because the question was. Oh wait, you had a question or I asked?
Sorry. When you're done, we have an additional question.
You have an additional question. Okay, so the reason why we can't relate value to the make of the car is because regression models require two numeric variables, and the make of a car is categorical. Okay, so we can't create a model for a categorical variable, right? We can't. It's not like Mercedes-Benz has this number value and Ford has another value, and I don't know, Kia has another one or something like that, you know. You said there was another question over there.
Yes. So the question came up as to, we see that in the formula,
Yes.
so y hat y equals a plus bx, b times x.
Yes.
However, that's an addition, that's a sum. However, when we're looking at it, we're looking at the 21,375 minus.
Yeah, okay, so
subtraction.
just, you have to think of this, okay? You have to think of this as exactly the same thing as plus a negative 1215, okay? So essentially this is what we have going on. It's when you see a negative minus 1215, we're essentially doing a plus a negative 1215. That's all that's going on. So that's why our slope is negative 1215, and et cetera, et cetera, et cetera.
Or, like, I just took an algebra class, like, if you put it in the parentheses, isn't it like multiplying the...
Yeah, I mean, we can also add more parentheses. We can do all of this stuff. We don't have to, okay? Like, the rules of math is just that, like, these things mean these things.
Yeah.
You know, if it helps you to add parentheses so you can see these things a little bit better, then by all means, you can do that. Yes.
Could this work with the value of like Mercedes-Benz stock?
Well, so the value of stock doesn't really follow a straight line. So our the things we're using here would not be a good way to model stock. We could model stock with another regression model, but not linear regression, because stocks don't really follow a straight line the whole time. Okay. Yeah. Okay. So anyway, let's say we make a prediction. So it says make a prediction for the value of a car that is 5 years old, and we predicted the value to be 15,300. Okay. So there's another concept called a residual. Okay. And this is just whatever model you have, because it's a model, it doesn't account for everything, right? You're just simplifying the world down into just a very simple representation of how things work. We're saying cars are going to be determined by how old they are. But that's only partially true, okay? Because there's a lot of other things that go into determining how much a car is worth, okay? So everything that we haven't accounted for, that is, we just kind of lump it all together in what we call the residual, okay? So if we find a car that's 5 years old, let's say it's worth only $14,000, okay? So we find a car that is 5 years old, you know, but selling for 14,000, okay? This means its actual value is less than what we predicted it to be, okay?
Is this part of chapter 4?
Yes, yes, it's still part of chapter 4.
It's not listed.
Under residuals,
Yeah.
there will be, well, I'll find it. There is definitely residuals here.
Page 664, which is not the same chapter.
Okay. The actual value is less what we predict it to be. Okay. This difference is called a residual. Okay. And so the residual is equal to the actual value, or actual y, minus the predicted y. So in our case, I'll use a different color. Our residual is equal to 14,000 minus 15,300. We get negative 1,300. Okay. All right. I think that covers what I want to cover for chapter 4. Be sure you do your homework, and I have a practice quiz online that covers a lot of these topics as
I don't see it
well.
all in chapter 4.
You know,
It's not, then what do we do? It's later in the book.
Okay. This is the example that I'm covering for residuals. Okay, it's this simple and straightforward, and I have an example in the practice quiz that covers this. there will be one question on the quiz covering residuals, and you just need to know it's the difference between the actual value of y and the predicted value of y. Okay?
I have a question. I work in